Jaroslav Hamerský, and he will talk about the oscillations of magnetized relativistic tori.
Okay, thank you very much. So first of all, I would like to thank organizing committee that I can be here today, and I will tell you about the latest results which we obtained with my supervisor Vladimir Karas. And for those who would interested in this topic, so this was published in Astronomy and Astrophysics in this summer. So if I had to say most concisely what we were interested in, so I would say that we were interested in the behavior of accretion torus in the vicinity of black hole. In the vicinity, it means that we deal with the radii, several Schwarzschild radii. And then we studied the influence of the magnetic field on the accretion rate and also on the oscillation properties of this tori. So what was the motivation for this topic? So I think that no one is surprised that maybe in every galaxy there is a supermassive black hole, and we know that in the center of our galaxy there is a supermassive black hole which mass is approximately 4 times 10 to the 6 of solar masses. So we have supermassive black hole with a very strong gravitational field, and then we know from the observations of polarized near-infrared radiation from the center of the galaxy that there is a strong gravitational field, strong magnetic field. So from these 2 points, we know that the interaction between magnetized plasma and strong gravitational field is very important for full understanding of the feeders, which plays important role in the galactic center. Okay, so what's our physical problem? So we have a black hole which induces gravitational field, and then we have orbiting plasma. So we have accretion torus around the black hole. So for the description of such system, we need general theory of relativity and magnetohydrodynamics. So our evolution equations we get from the conservation laws, like conservation of energy momentum tensor. Then we have continuity equation and also Maxwell equations. So we need to have a closed system of equations, so we have to prescribe some conditions. So we prescribe force-free constraint, which tell us that the electric intensity vanishes in the rest frame of the fluid, and then also we have to prescribe some equation of state. So we have closed system of equations, and we can solve it. So our energy momentum tensor looks like this, where it is rest mass density, U is density of internal energy, P is pressure, and B corresponds to magnetic field. If we do the corresponding covariant divergences, we get a set of these equations, which has to be solved numerically. For this purpose, we used the numerical program HARM, which was developed in 2006. Okay, so very important characteristic for accretion torus is its profile of density of angular momentum. It is very important because, as you will see later, so the profile of energy momentum tensor can stabilize or destabilize the torus against some sorts of perturbations. So when we need to create our accretion torus, or the stationary solution for the fluid which is orbiting axially symmetric around black hole, we get this solution from relativistic Euler equation, which follows from the conservation of energy momentum tensor also. So we get this equation which we need to solve. Here you can see that this equation can be solved easily analytically if this integral will vanish, because this is only function of metric tensors, and this integral can be easily solved for given equation of state. So, for example, when angular momentum density is constant, this equation is very easy to solve, and we can create the equation torus very easily. But if we want to assume also the magnetic field in the torus, so the equation, the Euler equation is complicated because there is one more term which corresponds to the magnetic field. It was shown that even the configuration when the magnetic field is present in the torus can be stationary, but the magnetic field has to obey this condition. If there is only purely toroidal magnetic field in the toroidal torus, and it satisfies this condition, so this configuration can be stationary. And if we prescribe some relation between these two integrals, it means if we prescribe some relation between thermodynamical and magnetic pressure, so we can solve this equation, and we have a stationary solution of equation torus, even if there is a magnetic field present. So the solution for given constants is presented here. Okay, so if we want to create our equation torus, we have to know the metric. So in most cases we used Kerr metric with spin which was ranged between 0.3 to 0.9, and then we need to know the profile of angular momentum. On this image you see the profile of Keplerian angular momentum, and this is case when the torus has constant angular momentum density, and this is case when the angular momentum density is increasing function of radius. Here you can see that the tori, which has different profile of angular momentum, has also different length or different. They can range different region. And this point, this is the inner edge of the torus, and this point where the angular momentum is equal to Keplerian angular momentum, this is the center of the torus. And in our cases, we used the accretion tori, which has a relativistic cusp. It means that it was the critical configuration for which at the inner edge is Keplerian angular momentum, or the angular momentum is equal to Keplerian angular momentum. Okay, so far we have stationary accretion torus, and now we do some perturbation. So we take some mass from the disk and give it to the black hole. It means that the parameters are updated of black hole. So the metric is changed, and now we want to see what will happen. Because if we change these parameters, so we do this perturbation, so the critical configuration is different from the previous case, because it can so far the disk was inside the critical configuration, and now because the Roche law or the Roche surface can be maybe shrinked or enlarged, so the disk can occur outside or inside, and it means that there can be some another accretion, or the accretion will stop. So it depends on the behavior of the critical configuration on these parameters M and A. Okay, so here you can see the cross section of our torus in the horizontal plane, and there is shown the rest mass density in the red color. So in the red color corresponds to the biggest value, and the purple to the lowest value on the surface. And this first image is at the start of our simulation, so it means at the time equal to 0. So there is no accretion. The configuration is stationary. But after some time, some mass is accreted and goes towards to the black hole. But the accretion, as you can see, is not monotonous, because after a different time it is almost stopped, but then it also increased and more mass is accreted. So you can see that the function of mass or the dependence of the mass of the torus on time is not is not monotonous, but there are changing phases with bigger and smaller accretion. On these two panels, there is a comparison for different spin values and for different angular momentum profile. So this solid line corresponds to the profile of angular momentum which is most steep. It means that the angular momentum is bigger than in these cases. So you can see that the bigger angular momentum is, the smaller accretion is. And another very important point is the behavior of the position of cusp as function of accreted mass. So there are three cases. The initial spin value was 0.3, 0.5, and 0.7, and there was mass which was accreted to the black hole, and the parameters were changed, the spin and mass of the black hole was changed, and then we looked how the position of cusp was changed. So in this picture, the solid lines correspond to the case when the mass with subcapillarian angular momentum was accreted, and the dotted case when the mass with capillarian angular momentum was accreted. And you can see that if the mass with sufficient angular momentum was accreted, then the position of cusp was moving more to the black hole. So the critical configuration was enlarged, and it has the consequence that the torus remains still inside the critical configuration. So this effect has stabilizing effect, because the critical configuration is bigger and bigger, and this is still inside the torus, or the torus is still inside this configuration, and so the accretion will stop. But in the case, for example, if there was some accretion with very small angular momentum, so the effect of enlarging the mass of black hole would beat this effect of enlarging spin, so the accretion rate would be bigger. Okay, so now we can look on the influence of magnetic field. On this plot, there is a simulation for the same parameters, but only this solid line is for non-magnetized case, and this broken line is for magnetized case. And the magnetized case was highly magnetized with the parameter beta 3, and beta is the ratio between thermodynamical and magnetic pressure. So you can see that there is an oscillation of central density of the torus, and you can see that the change or the difference between two cases is important mainly in the start of the accretion or in the early phases, because then these oscillations are almost exactly the same as non-magnetized case. So the magnetic field only change the property of the oscillation at the beginning, and then it plays no role. And on the right panel, you can see the oscillations of the center of the torus. It means on the radius where there is a maximal pressure. And also you can see that the magnetization doesn't have a really big effect of the oscillation period. And on this picture, there's a comparison of oscillations for different angular momentum profiles. So angular momentum is a function of radius as r to the power of q, and if the q is bigger, so there is a longer oscillation period, because this red line corresponds to the lowest q and green dashed line corresponds to the biggest value of q. Okay, so now we can look how the magnetic field influenced how much mass of the initial torus is accreted. So if the magnetization beta is big or high enough, it means that the beta is very small. So you can see that the time is very small, which we need for half of the mass of the torus be accreted. But then if the magnetization is smaller and smaller, it means that the beta is bigger, so the time is higher and higher, and from some value the increasing is not very important in this function. So it means that there is no difference between non-magnetized and slightly magnetized case. So the magnetic field plays important role only if the magnetization is high enough. So it means if the magnetic pressure is comparable with the thermodynamical pressure. And on this image, you see the function of time which we need to be half of the torus be accreted as a function of the slope q. So you see that if the q is bigger and bigger, so we need more time to be half of the torus accreted. So it's not surprising for us, because bigger q, it means that the angular momentum density is higher, and we know that the increasing angular momentum profile has stabilizing effect. Okay, so far we did the perturbation in the radial direction, so we did the radial oscillations, but we can also do some perturbation in vertical direction and get also vertical oscillations. And I think that it's useful to stress that these oscillations can be identified as radial and vertical epicyclic oscillations. But if we have thick accretion tori, so there is also another sort of oscillation which is caused by the oscillation of the disk or of the torus itself. It's a hydrodynamical oscillation. For example, if we perturb the rest mass density distribution, so there is a vertical and radial epicyclic oscillations, and also the it is called oscillation. This is oscillation which is called inertial oscillation of the torus itself. And if the torus is thinner and thinner, for example, in the limit of thin disk, so these oscillations are purely epicyclic oscillations. But only if the torus is thick enough, so the additional inertial oscillation is important. Okay, so what's our conclusion? So we did simplification because we assume axial symmetry. So we can't say anything about axial oscillations. And we know that if the angular momentum profile is increasing, so it has stabilizing effect against perturbations. And then that the influence of magnetic field is significant only if the value of magnetic pressure is comparable with the thermodynamical pressure. And oscillation frequency is influenced by the magnetic field only at the early phases of accretion process, because then the magnetic field play no role. Okay, so I think that it's enough from me. So thank you.